Yes.
Awesome. Okay. Hello, welcome everyone. This is our first live webinar, and hopefully not our last, but today we try to touch on the high-level concepts of what you need to sort of see and know to really have the right mindset to understand how we can solve climate change. This talk will be given by 3 of our team members. There are vast amounts of team members, though. We're not the only ones. We're over 80 people in climate science, but we're the lucky 3 faces that you get to see today. I'm Eric, one of the co-founders of Climate Science. I'm an author on energy and the CEO and chair, and did some research at MIT and Facebook AI and the Vienna University of Vienna. And did studied at the University of Cambridge. Pandora and Joe, do you want to introduce yourself?
Sure. I'm Pandora. I'm a content co-director and the author of the agriculture course. Previously, I graduated from biological sciences at the University of Oxford. I've also done various science journalism, and I work part-time as a science illustrator.
And I'm Joe. I'm the CTO, so that means I do all the technology software stuff for climate science. So I try and lead the team for the website, to build the website and the web app and all of those cool features that you can use and read the climate science content on.
Right. Okay. So that was just a quick introduction. And again, I want to just very, very clearly say that all of the content in this presentation is not just made by the 3 of us. This is made by a huge team of volunteers all around the world. These numbers are outdated. We're now over 80 from 17 countries, and all of them contribute heavily. So this is not just us 3, right? But after this, let's and you'll find a list of them on our website if you're interested, and you can join and apply there, by the way, if you want to join too. I'm now going to hand over to Pandora and stop screen sharing, and you are going to start screen sharing, right? And you can start the part on climate change.
Fantastic, thank you. Right, there we go. Can you see my screen? Does that work? Great.
Right.
So I'm going to talk briefly about climate change and predictions of climate change in the future. And then I'm going to hand over to Eric to discuss some of the possible solutions. So we've all heard about global warming, but what does that actually mean for us? So global average temperatures have been increasing over the past century and a half by 1.1 degrees Celsius, and that's a trend that's expected to continue. Scientists use different mathematical models to predict future climates based on different scenarios. And here we've got an example of that. So under the purple scenario, we have what is expected if drastic climate change policies are introduced. You can see even then, we're expecting some increase in temperature. But this green line is what we're expecting to see if no climate change policies are introduced, if we continue business as usual. And this shaded area on either side of the line, that's the uncertainty of the predictions. So how confident we can be in the accuracy of these predictions. And you can see it's quite a broad area. And that's because we have to make a lot of assumptions. We're predicting the future. But even so, in the best case scenario, it's still not looking great. And we're already starting to see the consequences of this climate change. So I'm going to look at the example of Arctic sea ice loss. And throughout the year, levels of Arctic sea ice, they change. So in the summer, the ice melts, in the winter, it freezes again. But if we look at a single month across several decades, we can see that the area of Arctic sea ice is steadily declining. And this has devastating impacts on local wildlife as well as wildlife globally, because it will affect the global weather patterns. And if this trend continues, scientists are expecting that we'll see ice-free summers in the Arctic in the relatively near future. And all of this is occurring because of increasing greenhouse gas emissions. So greenhouse gases, the gases that exist in our atmosphere that absorb infrared radiation from the sun and heat up our planet. Some of these are released naturally, but human actions have been causing the emissions of these greenhouse gases to increase exponentially. So you can see here that different countries contribute differently to these emissions. And the EU28, US, and China have a massive contribution. Whereas countries like India, which have a population of over 1.3 billion people, have a relatively small contribution. And that's the same with most developing countries, which is completely unfair because in most cases, developing countries are the ones who are going to experience the effects of climate change soonest and most seriously. So what's causing these emissions? Well, the biggest cause of man-made greenhouse gas emissions is carbon dioxide released from burning fossil fuels to make energy. There are lots of other causes of carbon dioxide emissions, as well as other greenhouse gases. So for agriculture, some of the biggest emissions come from methane and nitrous oxide. And the total of these emissions released globally comes down to the climate equation. It results from population, so how many people are on the planet, services per person, which means how much stuff people are using and buying, and the emissions per service. And to stop climate change, we need to get these total emissions down to zero, which means one of these other variables has to be zero too, because anything times zero is zero. So let's have a look at the options for that. Population zero, no people, not really an option. Consumption at zero, well, then we don't have any electricity, no farming, no healthcare, also not very feasible. So that leaves us with one option, getting the net carbon dioxide emissions per service, or the net greenhouse gas emissions, there are other greenhouse gases, to zero, which means that any emissions we release have to be cancelled out. So let's have a look at how these variables have changed over recent years. Population has been increasing dramatically. So at the start of the 1900s, we had a global population of 2 billion people. 2019, it was 7.7 billion. And by 2100, we're expecting to see a population of about 10.9 billion. Consumption, that's also been going up with just using and buying and doing more stuff. Now, emissions have actually started to decrease, which is great. But remember, we need to get net emissions down to zero. So they need to go down a lot faster than they are doing at the moment. So how are we going to do this? Well, I'm going to hand over to Eric now, who will talk through some of the potential solutions. And you can also check out our website, which is climate-science.com, which will also inform you through various other courses. So over to you, Eric. I'll stop screen sharing now.
Thanks, Pandora. That was great. I'm going to start screen sharing again and go from the current slide. Right. So when you solve any problem, you kind of want to approach it like with sort of a mindset that first you want to understand the problem really well. We just did that. Pandora took you through a lot of the sort of thinking, you know, where do emissions come from? These three variables, where can we attack them? We're not fully done with that yet. Then we want to see what solutions to that problem could really look like. And once we identified some potential solutions, we'll want to see what the missing pieces are. Why aren't those solutions out there? You know, why isn't the problem solved? If there is a potential solution, why doesn't it exist? And then step 4, solve them. So I'm going to be trying to take care of step 2 and 3. Pandora did step 1, and Joe will do step 4, tell you about how you can start contributing to these things yourself. First, though, and I want to use the YouTube chat function for this, please guess how much of all of the emissions, all of the greenhouse gas emissions coming from humanity are from energy. Energy is not just electricity. So it's not just charging your phone and your light bulbs. It's all of the fuels that you use to fuel your car, an airplane. You know, energy is needed to do pretty much anything. Heating, lights, all of this. So all of the energy together, but not stuff like meat and not stuff like What are other non-energy emissions if we burn forests? All of this is not included. But how much do you think is energy? Is it 14, 28, 56, 73? Am I just writing random numbers and it's something completely different? Let me check out the YouTube chat function. 56 is one guess. Let me see if there are more guesses. Right, so it actually turns out it's 73%. So when we're asking what the problem is that we have to attack first, we should start with the 73% and then start thinking about the other 27. I mean, we can do them in parallel if it's easy or if it's feasible. But really, one thing we shouldn't do is not look at the 73%. So this talk for this webinar, we're only going to look at those. The other 27 are very important too, and they have some other implications like biodiversity that are absolutely important for the planet and humanity. But for this talk, I just want to talk about the 73% because that's a lot. 73%, 3/4. All right, energy. Well, some question that we get a lot is, can't we just use less? Yes, we can use less in some rich countries like the United States, like Norway, like Iceland. They can go and use less. But why can't other countries use less? And why can't humanity on average use less? Well, there's this correlation where if you use more energy, then the Human Development Index, which is a number that indicates how good your life expectancy, your living standards, your education, and so on are in a country. And you can clearly see the more energy you use, the higher this gets. Now, it's not linear. You know, after, say, 5,000 here, this is just a unit kilowatt hours per person. Just think of it as just an amount of energy. But after that amount, it doesn't get much better. So we can stop there. But what we can't do is have people consume almost nothing. It's just not fair. So overall, the trend is that energy use will keep increasing for a while. And that's good because we don't want poverty. And that's good because we in the richest countries might think that our life is great, and it is, but we also use far more energy than people in other countries. If we want everyone to use a fair amount of energy, which means we use a little less, and other countries like India or countries in Africa start using a lot more, then overall the demand will increase. So how would we cover that? Here I'm showing how electricity generation will be covered over the next, and I realize I don't think you see this if I'm screen sharing. How electricity demand will be, God damn it. Why is it not? Here. Right. We have 2020 right now, and 2020, almost no solar and wind. Quite like a little bit. It's been increasing over the last years, but not that much. Lots of hydro, some nuclear, but most of it is still oil, gas, and coal. Now, if you just look at those three, at these fossil fuels, you know, the thing that causes CO2 emissions, that's what we don't want. If you burn it, CO2 goes into the atmosphere. That is going to decrease quite heavily. It's not predicted to go to zero, but what's so promising is that the growth in energy demand that is predicted to happen because the world energy demand is predicted to rise is coming from renewables. That's obviously not given by law yet because we can't know that into the future, but the current predictions are promising, and that's a good reason to be optimistic about the future. The current predictions are not that things are going to go bad. They are that things are going to be good in many ways. And one of those is that energy is going to become more and more sustainable. Now, you could argue it has to be even faster. We have to get rid of gas and coal way quicker, and that's true. If we could do that, that would be fantastic. But we're not at zero, and that's an important thing to realize. We can still improve, though. Now, one thing that is really motivating in terms of improvement is if you look at the price graph of installing a new solar panel. Now, you know, we all want to have 100% renewables and everything super clean, but you don't want to pay 10 times as much for it than you pay right now. It's just that nobody would really do that. If you're realistic, it just wouldn't happen on the scale we need it to happen. However, if we can make things like solar and the other technologies that we need cheap enough, and this has only happened in recent years, then with those technologies, we can implement policies and incentives that will encourage companies, even including oil companies, to switch to more sustainable alternatives. So one of our easiest weapons against climate change is making the sustainable option the cheapest. If we can make the sustainable option the cheapest, the market itself will want to choose it. There will still be some forces like the lobby and like the coal lobby or oil lobby trying to fight that. But if it's cheaper, eventually it should win. There are other ways of doing it, but this would be by far the easiest if we can achieve this technological advance that gets it so cheap that it's just a brain dead decision that we should be using it on a huge scale. And it is predicted that that is going to happen for renewables. Now, there's still some problems. You know, if you think of history as something you read in a book and the future as something you just don't know yet, that's one way to look at it. But I think another way to look at it is think of the whole story as one line, and you just get born at one spot somewhere in the middle. It's a journey that has been going on before you were there, and it's a journey that will keep going on. And you just have to kind of see and understand and analyze where on that journey you're at. 20 years ago was the time of the internet. That's when all of these amazing internet systems and services started to come into existence. That will not happen again. That happened one time. And similarly, right now, we are in the time of clean energy innovation. Clean energy is going to grow massively over the next tens of years, and there's still some open problems. It's not either done or nothing is done. We're in that procedure. And if you want to contribute to that, those are three things that are very important. There are far more, but we don't have time for all of them. They will be on our website. The first one is sustainable solar and wind. The second one is scalable energy storage. And the third one is clean and cheap nuclear. I will briefly touch on all of them. Now, sustainable solar and wind is in particular important because what are you going to do with the solar panel when it's past its lifetime? A solar panel has 25 to 30 years approximately of predicted lifetime, and you need to have some plan of what you're going to do with it once it's essentially not useful anymore. Are you just going to throw it into landfill? Can you recycle it? Today, we don't have a good solution for this. There are many kinds of solar panels, and there is no standardized recycling procedure. That's something we really need to develop. The same is true for wind turbines. There are other things like making it even cheaper, making it out of materials that are more sustainable to mine. And all of those research areas are very, very important and ongoing right now. Scalable energy storage is a little harder to explain, but this graphic does it quite well. If you want to use lots of solar and lots of wind, you can't choose when you get it. The sun comes at noon. Sometimes it's cloudy and it doesn't. But you want to use your electricity in the evening, in the morning, or really whenever. Now, when you produce more solar than you use, or the same is true for wind, but solar is easier to draw, then yeah, perfect. You can just use it, right? That's the light blue part of the curve. But when you use more, this is the purple thing, than you produce at a given time, you just don't have it. And therefore, you need some way to bring that big bulk of yellow down 6 hours into the future, bring it to the evening, and some of it to the next morning. Now, that's what we need energy storage for. And when I say energy storage here, I'm not talking about a battery like the thing in your phone or even the thing in your electric car. The amount of energy that you need to store to do this is absolutely vast. In fact, it is so vast that I'm going to make another quiz out of it. Now, if you wanted to store all of the energy that you use in one day, the whole world, every single person. So, we use a certain amount of energy every day. If we wanted to store this amount for 24 hours, and we wanted to do that with batteries, the same kind of batteries that we use in phones, that we use in electric cars, so the very popular ones, lithium-ion batteries, how much would that cost? Type it away in chat. I'm just going to give you a few seconds before I reveal the answer.
There's a 20-second delay, so
yeah, I know. I'm not going to wait the full 20, I think, just so that people have time to think about it. How much does a phone cost? What could the battery? Right. So the answer is, oh my God, nearly as much as the world produces in value. That's the GDP overall. So just to grasp this, $1 per person, nothing. Bill Gates' net worth, quite a lot. That's $10 per person on Earth. It's approximately his net worth. Not even $1,000 per person is enough. It's $10,000 per person to store your daily energy use for one day. That's not great. So what do we need? we need massive amounts of research in this area. Batteries, or whatever technology we choose in the end to store this energy, needs to be 10 to 20 times cheaper to solve this problem. That's not our opinion. That's the opinion of experts working on this, including at the University of at Stanford. So the technology, and this is a myth, is not there. It is just not here. When people say the technology to solve climate change is here today, that is not true. Some of the technology is here. The technology has been massively improving, but not all of the technology is here. We still need massive amounts of research and innovation. Some things are off by a factor of 10 and 20, as you see, if we were to use batteries. There are some alternative technologies that cost less but have other problems. If we can solve this, it will be way easier to solve climate change. But climate change is not easy. The solutions are not just there and we don't use them. Not all of them exist. Right, so what if that's not gonna work? 10 to 20 is a lot. What if we just can't do it? What if it's just too expensive? And you wouldn't want to pay $10,000, right? That's just not gonna happen, realistically speaking. So what could we do? What are our alternative sources for energy? And remember, 73% of emissions come from energy. So we need a solution for this. Of course, so this graph, what it does is it shows on the y-axis here, like up and down, it shows how many deaths you get per unit of energy. So coal kills a lot more people than oil, for example, and that kills more people than natural gas. And on the other axis, left and right, on the x-axis, we show the greenhouse gas emissions, so like CO2 per unit of energy. So clearly, both in terms of deaths and greenhouse gases, coal is terrible. Coal emits lots of greenhouse gases, and through air pollution, kills lots of people. Oil is a tiny bit better, but still not great. Natural gas kills fewer people, still lots of greenhouse gas emissions. Those are our three big fossil fuels. Now here, biomass is quite popular. Still not that great, actually. Unfortunately, not scalable enough to deploy it at anywhere near the global energy demand. Hydropower, a very popular renewable source of energy. In fact, the most popular renewable source of energy today, is far more sustainable in the sense that it causes fewer greenhouse gas emissions and it causes almost no deaths. Unfortunately, the world doesn't have enough mountains and doesn't have enough, well, rivers with mountains to fully fuel itself with hydropower. There are some countries like Norway that run on almost 100% hydropower today, and Iceland runs on almost 100% geothermal. But other countries they're just flat and they can't do it. Unfortunately, they just don't have the right type of land structure. Now, yeah, here you see, and you probably by now get where I'm going with this if you looked at this graph. Wind and solar are awesome, don't cause deaths, don't cause greenhouse gas emissions, but right there with them, you find nuclear energy. And this might be counterintuitive to some people. And I understand why. You know, if a nuclear reactor explodes, you would think there are lots of deaths, there's lots of destruction. And that's true, some people die, and there is some destruction, but it's not that much if you really look at the numbers, and it doesn't happen almost ever. It happens, you know, very, very rarely, every 10 or something years. Whereas with coal and with oil, you have continuous air pollution, which continuously and slowly causes deaths. And that's just something that doesn't make the news. But you could equally write a news story saying so and so many thousands of people died every day because we use coal. But instead, we don't do that, but we do write a news story every 10 years saying that there was an accident at a nuclear plant. Now, this is important, and it's important to be open-minded to these things because we really want to solve climate change. This is not the right time sort of to exclude options, especially if they score so well. So let's look at it. Let's look at it. In fact, nuclear has such low emissions that if we only used nuclear to make our energy emissions would be down by 98%. So of those 73%, we could reduce that by 98%. Out of those 73. So that would be almost gone. Right. How does nuclear work? Why does it explode? And what are the problems? It's going to be very short, but I want to briefly talk about it. Just because so many people have this, and it's very reasonable given how the media portrays it, have this fear of nuclear, but it's really just a technology that you have to build right for it to work. So in a simplified way, how it works is you have uranium, uranium-235, a radioactive material, in a container that heats some material that can be, most often it's water, and goes in a circle. So it's really just a very, very fancy way to boil water, if you look at it that way. So this gets very hot, this orange circle. Then when you heat this orange circle, and again, this goes in a circle, uranium, this radioactive reaction that happens, you know, the atom splitting, that simply creates heat. That's how we get energy from nuclear. Splitting atoms makes heat. And that heat heats up the water in this orange circle. And this orange circle, again, goes through another circle, another circuit of water. Those two are separated for a few reasons. Some of them are technical. Some are just that you don't want radioactive water to be in too many places. So it's in a way, it's cleaner. But there are other reasons too. But anyways, this orange water essentially warms another bucket of water. Here, the secondary circuit, the blue one, which then spins a turbine and works very similar to the way coal plants work here. Coal plants, they also just heat up water, and that water spins a turbine. Now, the difference is instead of burning coal, we have atoms that split. There is no CO2 here. That's the important part to realize. Now, nuclear waste is important, and we'll get there. But there is no CO2. The only CO2 emissions that you get from nuclear is building the thing and getting rid of the thing when it's after its lifetime. And sort of these indirect emissions, but there are no emissions during the process, and that's great. So why does it explode? It explodes when the cooling mechanism doesn't work, and when the reactor overheats and the pressure gets too high. When the pressure gets too high, the materials and pipes and tanks just burst, and we don't want that, of course. There are a few ways to fix this, actually. And in all of the historic accidents that happened, it was clearly an engineering problem that could have been prevented. However, that, again, is not necessarily a good excuse, because you can never guarantee that there is no engineering mistake. However, recently, since in the last decade, there have been reactor designs that simply, no matter how much you mess up, they will not explode. They will shut themselves down whenever it gets too hot. So with new reactors, if we built new reactors today, they would be safe. They would not be able to explode in any reasonable circumstances. In fact, researchers and companies simulate things like earthquakes, tsunamis, even bomb attacks to make sure that nuclear reactors don't explode if they happen. Because of course, it's not even good for their business, right? They don't want them to explode. They want them to never explode, to have any sort of viable business option. So they try their best. Right, but there is this one problem that is super real and that we do need to deal with, and that's radioactive waste. There are a bunch of types of waste. We won't go into that too much, but the radioactive waste that we need to store for thousands of years is a big deal. And that truly is a big deal. And we don't have a long-term solution for it yet. That is true. The explosion part is not so bad as people think, but radioactive waste is a problem. There are ideas that would potentially allow us to reuse that waste as further fuel. So you could make more power out of your nuclear waste and make the waste less bad in the process. But that technology doesn't yet exist. There are ideas, concepts that should work and that do work in theory, but we haven't built it yet. Now, that's another point where we just need more research, and it's the same story. You know, if we work on it, we get there, it's going to get better. But even if we don't solve that, we have to weigh our options. You remember the graph Pandora showed you with the emissions going to somewhere between 3 and 12 degrees, the temperature going 3 to 12 degrees up. Now, we have to compare that to the nuclear waste. It's not nuclear waste or no nuclear waste, it's nuclear waste or coal. And if you weigh them, you should get the answer to be that you should be using nuclear, right? Even with today's technology. But future technologies are trying to improve things such as waste and make them even safer and so on. There is a lot of potential there. It's just not being worked on enough. And I highly recommend, if you're interested in this, read this report, The Future of Nuclear Energy in a Carbon-Constrained World. It's very interesting. Thinking far ahead into the future and trying to see if and where nuclear would fit into the solution there. I really recommend this read. Okay, that's it for my solutions part. Soon, Joe is going to speak a little bit about how you can start contributing to all of these things and how to find your spot in climate solutions work. But I quickly just want to those that haven't seen it yet, guide you to our platform, solve.climate-science.com. if you're interested in the things that we've spoken about and way more, this is just 5% of what we do. You'll see lots and lots of these courses coming out in the next few months, covering all of these topics in depth, but trying to make them understandable using Earthly and using other cute illustrations. So check that out if you haven't already. Cool, I'm gonna stop screen sharing now. Thank you for listening, and I'm gonna give it to Joe now, who's gonna cover the third part of this talk.
Yep. Thank you, Eric. Can you see my screen?
Not yet.
No, sorry. There. Wait, so, oh, sorry, I forgot to click share. That is why. There we go. Can you see this?
Yes.
Okay, great. So I'm going to talk about high impact careers. And what is high impact careers? It's basically just what you as a person can work in order to maximize your impact on the world, basically. If what you want is to make a big difference, then what I'm going to talk about could really be useful for that. So this talk is mostly for young people who are thinking about starting their careers or researching what they'd like to work in, but it's also for people who want to, who might be parents or who want to advise other people who could be starting their careers. So when talking about high impact careers, which options are best for you, it really just depends on your situation, skills, values, and so many other factors. So there really isn't a one solution fits all to how to have a high impact career. That's why it's really important that you generate your own personalized list of potential high impact careers that you could have. So right now, I'm just going to present quick 5 steps that you can take in order to start thinking about high impact careers and get like a smaller list of options for you, really. So step 1 is to choose 2 to 4 global problems that you believe are really pressing. So this could be climate change, as we've been talking about, or it could be food security, gender equality, biosecurity. There's so many different problems that are very important and that you could choose to focus on. So right now you need to pick basically a handful of them and say, this is what I'm going to look at in the next 4 steps. So once you have these options, what you're going to have to do is identify the bottlenecks in that area. So that could be a lack of funding, a lack of new ideas, a lack of awareness, a lack of political will to change things, leadership. So those are so many different bottlenecks that we could have. So right now, as Eric was talking about with reducing CO2 per services, we really need more people having new ideas on how to basically reduce those services, the CO2 per service, sorry. So that's just to give an example. So once you have like those bottlenecks, you need to figure out how you can address those bottlenecks. And so that's kind of gets a bit more personal and quite difficult, but you have to figure out what kind of work you could do to address those bottlenecks. So that could be direct work. I don't know, in the case of research, it could be actually becoming a researcher and doing that research. You could also decide, I want to take an entrepreneurial path, create a new company that is going to focus on the research. I want to go into politics to be able to advocate for that, for research. Or I even just want to go do a completely unrelated job, make a lot of money, and then donate all that money to that bottleneck, basically. So that's really like the important part, is figuring out where you can have the highest impact on that bottleneck. So once you have all of those and you kind of know, well, this is an important field to work in, this is where I think that it's important to work in that particular field, you need to start ranking it for personal fit, because it's not your friend, your neighbor, your brother going to be working on that. It's potentially going to be you. So you need to say, how good am I going to be relative to the average person in that field? Because in some fields, it's natural. Anybody would be in that situation. In some fields, you would just not be as good as somebody else. So you should say, maybe I'm not going to go work in that field because I'm just not going to be good at it, or I'm just not going to enjoy it. But in some other cases, you could say, well, I would really enjoy this, and actually I'd be really good at this. So maybe you should prioritize those options. So that's really a very personal choice, and you have to self-evaluate yourself and say, what am I good at? What am I not good at, objectively? And then you can figure out which field you want to work into. Once you've gone through those steps, all these steps, hopefully you should have a shorter list of options, and you should be able to pick which one of those you prefer. If you don't have a shorter list of options, that's completely fine. It happens. It takes time to choose a career option. So you just need to go through those steps again and just do a bit more research, be a bit less, I don't know, a bit less picky about certain options or things like that. So if you're going to take anything, remember anything out of this, you should remember this equation, is that the impact you can have is really depends on the urgency of the issue you're working on, how effective what you're working on is. So this is basically the bottleneck and the career path in that bottleneck. And finally, personal fit. So how good of a fit you are with that specific field relative to the average worker doing that thing. And if you consider all three of those points and you go through the list I gave you previously, then I really think that you can be on the good path to having some good ideas about a high impact career for you. Once we've covered that, I think we're nearly ready for the Q&A. I'll just give the screen back to Eric if he wants to add anything. Yeah.
Right, no, I think we're good. Christian, let's just share the grid view as Pandora suggested, just with the four of us, and let's take the questions. We had some questions submitted on Instagram already, I think. Let's get the list up and start with those. In the meantime, if anyone else has any questions, we'll try our best. We might not know the answer to all of them, and we will say if we don't. But feel free to fire any questions, climate change related, climate change solutions related, impact careers related, at us. And if we feel comfortable answering them, we'll try to do it. And if we don't, we'll try to find someone on our team who is, and get back to you with the answer later. Right. I'm just getting up the list of questions that we got previously.
I've got them.
You got it.
Online. Do you want me to start with the animal agriculture one?
Go ahead.
Great. So one of the questions, well, actually two of the questions we received were about meat consumption and animal agriculture. So the first was, I'd like to hear more about the impacts of animal agriculture on climate change. And the second was, how can we bring about the cultural change required to reduce meat consumption? So I'm going to try and answer both of those at the same time. So why is animal farming bad? Well, different animal products do have different environmental impacts. So beef, which is the worst animal product for our planet, even low impact beef, even when it's farmed in the most sustainable way possible. But on average, 295 kilograms of carbon dioxide equivalents are released per kilogram of protein from beef. Compare that to chicken, which is only 35 kilograms of carbon dioxide equivalent per kilogram of protein. Now, that is still more than plant-based alternatives like chickpeas or lentils, but it does show that you can't really put an umbrella over all meat products being equally bad, because that shows they're not. So where are these emissions coming from? Well, with beef and sheep, goats, so animals we call ruminants, a process called enteric fermentation occurs in their stomachs when they break down hay, straw, and that's because there are certain microbes in their stomach. And these microbes release the greenhouse gas methane when they break down their food. And then the cow, sheep, or goat will burp the methane out. And that's a huge contribution to the agricultural greenhouse gas emissions. It's 44% of the emissions from livestock farming. Animal manure also releases greenhouse gases, so methane and nitrous oxide, which are both more powerful than carbon dioxide in terms of their greenhouse gas effect. And also the land use, so animal feed, I think 41% of the emissions from livestock farming come from producing the food for the animals. And that's quite a good area to target reducing the emissions from livestock, from animal farming, because if we can use food waste or insect babies, the insect larvae, we can considerably reduce that 41% of the emissions. So on to the second question, how can we reduce this consumption? Well, raising awareness of the impacts of different meats is super important. A lot of people are surprised that I say beef is so much worse than chicken, and that's just not a commonly known phenomenon. So it's good to increase awareness of that impact. Secondly, improving meat alternatives will help a lot of people who are sort of, oh, I want to reduce my meat consumption, but also I really like chicken. It'll help a lot of those people incorporate more sustainable proteins into their diet. And also, as well as improving the taste of these meat alternatives, we want to improve the price, because a lot of the time, not all the time, but a lot of the time, a vegan diet is more expensive. So if we can subsidize these meat alternatives and even introduce taxes on meats, so the price of food corresponds to its climate impact, that could also help reduce emissions. So I hope those two questions have sort of been answered with that.
Yeah, that was fantastic. Lots of numbers. That's always great.
They're over my head from the
yeah, I love numbers. I mean, right. I'm going to take one from the chat now, and maybe we go sort of back and forth between the ones that were previously asked, because the people who asked them in the chat are definitely here. So the one that was posted here is, there is no way, that was the first one in the chat, I think, there is no way to give back the pieces of the solar panel and make it useful again. That's a very good question. So is there a way to recycle? Yes, there is a way to recycle. It's just way too expensive, and it's not scalable. Right? If you think about the amount of solar panels you need, and we actually calculated this, you have to make some assumptions, so you can get different numbers here and there. But if you roughly sort of think about how big is the area of solar panels that I need to power the world, and forget all the energy storage problem, right? Like, just ignore that, act as if it didn't exist. How much do I need? If I could just use it right away, how big would the area need to be? Well, the answer is Germany. The answer is it needs to be as big as Germany, which isn't that bad. We can afford that. We use half the world's habitable land for agriculture, so we can afford Germany for energy. That's fair. That's not the problem. But the problem is, if you have Germany full of garbage after 30 years, and you have that every 30 years, you kind of have to do something that's scalable. You can produce solar panels in a scalable way. You just have lots of machines in parallel to do the same thing. But taking them apart and reusing the pieces in it is very hard to do on a massive scale for little money. That's the problem. It's just too expensive, and it's hard to scale. So, but yes, we could do it theoretically for most of the materials, at least. Do we want to take another question from, I hope this was sufficient, by the way. If any of the answers are not satisfying, just post another question complaining about the answer. Pandora, do you want to do another one from the list, or should we just do all of the chat ones first and then do the list? Maybe, because the chat ones are definitely here.
Yeah, let's take a few more of the chat ones.
Okay. So Christian is kindly posting them all in our Zoom chat. So let's just take them from here, and I trust that Christian sort of catches them, right?
Yeah, Eric,
right.
do you want uranium?
Yeah, uranium. I guess that's me again. Sorry. I hope we have some agriculture ones too. Otherwise, you're just going to do some agriculture ones from the list, and Joe mixing it. Well, uranium mining. I love these questions. I love climate science. We have such great users. Yes, what about emissions created from mining for uranium for nuclear energy? Is there a solution to making consequences of mining less severe? Emissions from mining are not that big of a deal for nuclear. All of the life cycle counted in, the emissions of nuclear are really just 2% of our current energy mix. So for each unit of energy. So the emissions don't need to be reduced further. They are extremely low. They are literally 1/50th of the emissions that of the way we produce our energy today. 1 divided by 50, as much. So there's no real need to reduce them much further. I'm sure there's some way of doing it, to getting it down, instead of 2%, 1.5%. But that's not what we should be focusing on here. However, there are some consequences of mining. And in fact, Uranium-235 is extremely both costly and difficult to produce. You need to mine natural uranium, which is mostly uranium-238. And by the way, if those numbers don't mean anything to you, what these numbers mean is essentially the number of protons and neutrons, which are super small particles that make up atoms. You know, everything in our body is made of atoms, and nuclear energy basically just means atoms splitting. And these atoms splitting, these things they split into, they're made of little parts called protons and neutrons. And 238 means there are 238 such protons and neutrons, and 235 means there are 235. In nature, most uranium is 238, and we need more uranium-235 to make the nuclear reactions happen. And the process of getting that out is very costly and very difficult. But you know, maybe you remember that slide I showed where we had two mountains of nuclear waste. The one was the radioactive one, which is the material after use, but the other one, the depleted uranium, that's what remains after we filter the 235 out. We get some mountain of uranium-238, and that uranium-238 can be used in a separate type of reactor, completely different to the one that to the ones that we use today. Without any mining, it's already there. We have fuel for over 1,000 years if we use that just the depleted uranium that we've produced just with our current nuclear reactors. With a fuel for 1,000 years into the future, without any mining, if we develop this type of reactor. Companies have been working on this. There is a pilot project by a company called Hydropower that should have been working by 2022. Unfortunately, the disputes between the US and China slowed this project down, and it's currently on hold. But it's very, very interesting in terms of research in the future of nuclear. I know this is a little more information than just about mining, but I think these sort of additional perspectives, especially with nuclear, are really important, because it's important to see that there is stuff about nuclear that's way better than most of us are aware of. And nobody talks about it. There is no way that people would know about it because the press just doesn't like it. Right, I think we have a question about education that Pandora wants to take.
Yes, so we've got no, that's the wrong one. How to make engaging content about climate change, and how to make my content reach people, and any tips. And really, you can make engaging content about climate change through any medium you want. Social media is a great way of getting the content out there. We've definitely found that useful. And I think trying to use different media, not just social media, but any kind of media, is a really good way of engaging different groups of people. So Instagram was somewhere where there wasn't already a huge body of scientific literature that was being translated in a fun and engaging way. So that's where we slid into that niche. And there's so many niches across education where you can talk about climate change. And really, I think translating complicated scientific literature into something that's engaging and educational and fun to read is so important in getting people to really understand these complex scientific concepts and realize that it's something that is interesting and that is accessible to everyone, and that we all really need to learn about it. So my tip would just be to read those papers, try and translate them, and try and disseminate them anywhere that you think there's a gap.
I'll take the question about landlocked countries. How does climate change affect on the ocean, affect the landlocked countries, particularly in Central Asia? So I can't say that I'm an expert in Central Asia particularly, but I do know that basically one of the big impacts of basically global climate change on landlocked countries means an increase in desertification and a lack of fresh water supplies. So like periodic droughts, reductions in water tables, things like that are especially problematic in landlocked countries. because of their lack of access, basically, to fresh water often. So, for example, Botswana has that big problem. It's a landlocked country in Africa, so it's definitely not Central Asia, far from it. But they basically have been facing these problems in recent years of climate change, meaning that they have less access to just like water, and it's especially important for their agriculture. And when you're talking about developing countries, this is even more important because it causes famines and poverty, which then leads to mass migration and things like that. I can share in the chat a paper by the UN Organization for Migration about basically the effects of climate change on landlocked and developing countries with regard to migration and desertification, because it's definitely a really interesting topic yeah, thank you for bringing it up, basically.
Awesome. I'll very briefly take the question about how much uranium we have left. Another amazing question. Yes, we will eventually run out of uranium. That's true. We would likely have enough uranium to get through the next few hundred years and make it. In the meantime, it is very, very likely that we would be able to develop a technology that can sustain us for many, many thousands or even millions of years. Potential technologies just include simply renewables, even nuclear fusion, which some of you might have heard of. I'm not going to go into that in depth now. That would take way too long, but we will have content on it. But that will take more time, but might eventually get there. And there are some other ideas too that might work with time. If we can buy ourselves a couple hundred years, that's by far enough for now. If you tried predicting 2020 in 1820, you would not have been right, I'm pretty sure. And if you try to predict 2220 now, I think you also won't be right. So if we can buy ourselves time until then, should be fine. We don't necessarily, the idea that we need sustainable energy forever now, I don't agree with that. I think I agree that we will eventually need it, but now we just need time so we don't get 12 degrees warming by 2300 or whatever the upper bound of that graph was. That's just what we want to avoid for now. And we want to buy ourselves and our researchers the time to develop technologies that can truly fuel society for millions of years. Right, what other questions should we take?
Oh, before we answer any other questions, I just want to say thank you to,
yes.
is it Anastasia? If I'm saying it wrong, I'm really sorry. You can say in the comments that I've pronounced it wrong. But yeah, thank you for saying that vegan diets don't have to be expensive. You're completely correct. If you just eat plant-based foods, lentils, chickpeas, they're all really cheap. I was more talking about how we can convince people who currently have a meat-based diet to switch to more plant-based alternatives. And often the fake meats, they're the ones that are more expensive, and they're the ones that we should subsidize to try and convince people to adopt more sustainable diets. But yeah, thank you for your comment.
Right. So I'm just going to very briefly touch on, so there's one question I think that I should be by Beatrice. But first, Julia Proto asked, when did you come up with the idea to create climate science and how did you three make it happen? It was not, first of all, it's not just the three of us. We're just three faces that you see today, but the content and the information and the platform and the Instagram is run by 80 people. So that's 80. So we are just the ones giving this talk. And I hope next time there will be more people able to speak. I think all of the team members deserve a voice. So it's not just us. We're fueled by volunteers who contribute different parts of climate science. If this was just me or just Pandora or just Joe or even just the three of us, it wouldn't be anywhere near this good. The reason why we're able to produce content the way we do is because we get perspectives from very different people with different sets of expertise, with different perspectives on life. And together we manage to find something that we hope is close to the truth. You never get to be 100% right, but we try our best. And so it's not just the three of us. How did we came up with this? So this is a story back in the University of Cambridge when I was a student. I literally Googled how to solve climate change. I'm a machine learning researcher by trade, but I wanted to transition to climate change. So I Googled how to solve climate change. I did not find an answer that was satisfying enough. So together with Isabel Key, the other co-founder of Climate Science, we basically just started creating these Q&A things and decided they're a very good fit for Instagram because they're very visual and they're very it's just something that was missing. And simultaneously, but mostly me, learned a lot. She already knew most of the stuff, and that was a great journey for the first few months. And you might remember from Instagram that when we had this old style with the cartoons, before we had the more professional sort of graphic design illustration style, that was that time. And afterwards, we just started scaling the project up. Now we're trying to go to schools internationally next school year. And deploy a few more projects. But all of those updates are going to come on Instagram anyways. But yeah, it's not just the three of us. It's a lot of people doing very hard work that very much deserve to be mentioned. It is not just us. Okay, right. So last question that I should take, thank you, Christian, for pointing that out, is do you believe, and I will give my personal opinion on this, do you believe personally that we can actually achieve carbon neutral by 2050? That we can stay below 2 degrees Celsius temperature rise? And if not, should we also be hardcore investing in mitigation measures? Right, so these are three questions. Do I believe we can achieve carbon neutral? Do I believe we can achieve 2 degrees? And do I believe we should be investing in mitigation? Firstly, I think with the last question, you mean adaptation potentially, which just means adapting to things that we can't prevent. Mitigation is reducing CO2. So let me tackle those three questions. Do I believe we can reach carbon neutral by 2050? No, I don't. That is my personal opinion. You asked for a personal opinion. Other people might have different opinions. I don't think we will reach carbon neutral. I think we will reach a carbon decrease, and we will reach, we can reach very low carbon. The reason I don't believe in carbon neutral is because the carbon subtraction methods, as much as people love trees, they do not work. Trees are not a tool to remove CO2. They are a tool to lie to yourself. They draw carbon down and then they release it back up. If you count a tree as carbon removal, that is essentially just putting numbers in a balance sheet that have very little to do with the truth. Usually, you can keep a forest up, but it won't be at the scale and won't be at in the way that is currently being done by states that produce that plant forests of one species that is often simply just used as wood for any purpose in industry afterwards. So that is not a fair way of carbon removal. There are other ways like soil restoration. And you might have heard of the technological approaches like filtering CO2 out of the air. It's something that I was very hopeful about until about half a year ago. And when I actually ran the first principle numbers on this, it is likely not going to be a thing that we can do in any time frame less than a few hundred years to draw down the CO2 that we have emitted already. It is just too costly and it is too much. You really have to think of it as having as much oil and gas that we've ever produced unproduced, but unproducing is harder because you have to filter it out of air instead of just drilling a hole and oil comes spilling out. You're really comparing oil spilling out with filtering molecules out of air and storing them somewhere. This does sound harder, and it is. So unfortunately, I personally, based on the analysis that people at Climate Science have done, my interpretation of that is that any form of carbon removal is by a lot unrealistic. That's why I don't believe in carbon neutral. And that's why I also advocate strongly for not thinking too much about removal, but thinking about reduction, reducing CO2 emissions, getting clean energy with no emissions, not just capturing those. Right, so no carbon neutral, but we will get to lower carbon. Do I believe in 2 degrees? I don't think I think we're not going to be that far off. We might get 2.5 based on the numbers that if McKinsey is right, the prediction I showed with the predicted change in electricity use, and if some other things go well, like for example, electrification of vehicles, if we develop efficient hydrogen storage for airplanes and ships, if we manage to have convincing meat replacements or lab meat that people are willing to consume at scale, and we get rid of beef, if we manage to do all of this, we might even get to 2 degrees. But this really sounds difficult, and it is. 1.5, I would bet 1,000 billion to 1 that we will not reach 1.5. That goal is unrealistic. We will pass that, I think. And striving towards it is great, but I think having a realistic goal is even better. And you can always do better than your goal. I think a good goal to have is 2 degrees. It is very hard, but achievable. But more likely is 2.5. And if we really mess up, it's going to be 3 to 4. If we keep doing the political things we're doing now, it's going to be far higher. But I believe in the sense that in the next decades we will get better in terms of innovation is promising. So I think 2.5 is realistic, right? And I'm going to try to keep this short. Should we keep investing in mitigation? Mitigation is essentially developing clean energy. So yes, we should be massively pumping money into stuff like clean energy research, into meat replacements, into DNA, and this is something we didn't go into, GMOs and so on. They can really help poor countries. We might be scared of some of the side effects that you've heard about, but again, if you look at the numbers, they're actually good. There are just some companies that are, you could say evil, trying to maximize profit at all costs. That is awful. But if you use the tool in a bad way, you will get a bad outcome. If you use the tool in a good way, you will get a good outcome. And GMOs, for example, can really help people in Africa cope with the consequences of climate change. And that's something we should be dealing with. That's something we should be investing in as well. There are a lot of things we need to invest in, but mitigation is definitely at the top of the priority list. And we should at least double or triple that budget over the next decades.
Shall I take the how can we make farmers stop producing animals, or what other options do they have? So I guess sort of a two-pronged attack on this. So firstly, we can reduce the impact of livestock farming, animal farming. So one way is to stop overgrazing. So when cows and sheep overgraze on a field and chew up all the grass, then any carbon that's stored in those plants is released into the atmosphere. Whereas if we have fewer cows on that same field, and maybe we rotate the cows between different fields, then we're less likely to destroy as much of the grassland. And actually the grassland can be used to store carbon. Other things, like I mentioned earlier, we can change the animal feed. There are some cow breeds that just release less methane than others. And there's also adapting your diet to include more sustainable meat alternatives. So lower impact meats like chicken and other animal products like eggs are also low impact. But in terms of alternatives, so there's the vegan options we have today. So traditional options like chickpeas and lentils that I've already mentioned. Also innovative fake meats, alternative meats. So the Impossible Burger, that's gaining a lot of attention.
It's so good. It's so good.
I unfortunately haven't tried it, but you can
love it.
Lots of support for that one.
North America perks.
Yeah, there's I think there's a alternative egg product, there's alternative milk products that actually use the proteins from milk. So all of these alternatives are beginning to come to the market, beginning to be more scalable and cost effective. And then there's also new exciting alternatives. So I don't know if any of you read about the solar foods that came out earlier this year in an article. And what they're trying to do is create protein using bacteria and, well, thin air, according to the article. That's not quite accurate. What they do is they split water using solar energy into oxygen and hydrogen. And then the bacteria can use the hydrogen as well as basic nutrients and nitrogen and carbon dioxide from the water to make protein. And this is more efficient than plant protein, let alone animal protein. So we've got all of these really exciting innovations on the horizon, and the agriculture course, which should be coming out relatively soon. If you keep an eye out on our website, climate-science.com, there's a lot more information about the different alternatives we have and also how we can make farming more sustainable in the long run. So I hope that answers your question.
Right. This is a very easy one. Do you think the investment in renewable energy post-COVID-19 economic slowdown will go down? This will highly depend on the country. The global answer is difficult to predict at this point. Still, it was even harder to predict a while back, but I don't feel comfortable making a yes/no prediction now. But I can say that it will in the Asian countries have a far lower impact than in other places. However, an important aspect to consider anyways is that when I showed this bar chart, you might remember, with solar and wind massively growing and oil and gas staying quite big, coal slowing down and coal shrinking, that gas that stays is largely in areas like North America and Europe, and regions that already have infrastructure. So our investment in renewables is in many ways less important than Asian investment in renewables, because they are the ones still growing their energy use. Energy use in the European and North American countries is likely to decrease due to efficiency improvements in technology. We already have the infrastructure. It's very unlikely that we will turn off coal plants, as much as I would hope to. Once you built it, you paid for it, and then using it is just, you got to pay for the coal and the workers, but it's there, so you paid much of the cost. Therefore, it's difficult to say what's going to happen in Europe and North America. I think Asia is going to try to follow a very well, some countries are going to try to follow a more sustainable path anyways, largely for economic reasons, as well as, again, the easiest way is to just make things cheap. But there are still some sort of voices, and I'm not an economics expert. This is just from what I've been reading, a summary, essentially. Some voices are still saying that there is an issue that we might, it might decrease. We will really only know probably by the end of this year, fully certain. I don't even know if the countries have decided that. There is a risk that it will decrease for sure. The overall impact is certainly negative of COVID, the overall impact on budgets. Renewable energy might be an exception. Fundamental research on new technologies is decreasing. That is pretty much for sure. Some companies are increasing because it's going to increase their margins, their competitive edge, not their margins in the future, but most are decreasing it. They're focusing on their core business, basically what gives them money now because they need to survive. Nice. What is the next one? I think that one is Joe or Pandora or I who should take the social carbon one. Social cost of carbon.
I don't know.
I don't think I know enough to really have a proper opinion on this. I mean, I'm mostly energy guy, so. Christian, I mean, it needs to be scientific.
And a shortly step in. Well, regarding the social cost of carbon, if you see it as the external cost of the
if you want to show your video, people will see the magic behind the black square, which is totally a message, by the way.
So social cost of carbon in the sense that there will be future costs based on either damage or more costly ways of doing things. And especially loss and damage is a tricky question, which is also always a topic at the Conference of the Parties, the so-called COPs. So these climate conferences, which should happen once, or which have happened once a year, but this year because of COVID, there will be none, and it was postponed now for 1 year to next November 2021 in Glasgow. And social cost of carbon is something, when you look at the Nobel Prize Bill Nordhaus got in 2018 for his economics Nobel Prize, for his calculation regarding the economic optimum between abatements, or what can we do now to prevent climate change and investments and the damage occurring later on, and do model it then economically, so you can then get different answers. I personally don't like Bill Nordhaus' optimum curve, because this leads us to 3.4 degrees centigrade by 2100, and I think this is far too risky, as there are certain tipping points waiting on us, and if we tip them all, then the temperature raise will not be stoppable anymore. So regarding the social cost of carbon, I think there should be better economic modelings which show the actual cost, in a sense that future damage for the current generation should be included in economic evaluations, so that it gets clear, especially with loss and damage. It's not so easy to calculate the value, but we should give it a try to make it more clear that some things should be prevented, and this would also be economic viable. So, and especially for your young ones, I think, especially the young economists among you, you should give it a try.
Right. That's a very important point. And if you look at our climate predictions course, that's already on the, by the way, if you're wondering who Christian is and why he suddenly appeared behind a black square, Christian is, we're a charity, a registered charity in the UK, and Christian is one of the trustees of that charity, and does all of our like legal stuff because we are not really capable of that otherwise. So, right, you mentioned an important point, tipping points. This concept might not be familiar to everyone. Like if you think of the Arctic again, that graph that we showed, that Arctic ice is decreasing, it might not be possible to ever increase it again. That's, for example, that would be a tipping point. There are other things like once a forest turns into a desert, it's very hard to turn a desert back into a forest. And these problems, these tipping points, and that's actually a big deal for the Amazon rainforest, that we just don't know when it's going to happen, but we're pretty sure that sometime, but we don't know how hot it needs to be, at some point it's going to happen, and then suddenly, oops, the Amazon is gone. That'd be a very big problem. And we're not sure when these will happen. And the problem with not being sure is that policymakers and politicians, they don't, Christian, if you could mute yourself, yeah, I hear some background noise. Christian, the issue with policymakers and politicians is that they do not like uncertainty. They don't like, oh, it will happen between 1.5 and 4 degrees and we have no idea when. So they just ignore it. And even the leading climate projections that are being used for policymaking, they often don't consider these tipping points. And that's something we clearly need to change and need to consider in any social cost of carbon. I just wanted to add to that. You can learn more about this on our climate predictions course on the website. That's already done. Read it. Very, very good. Written by Hazel Ransom, one of our authors. Really, really, really good. Okay, we have more questions. You want to, you take cultured meat, Pandora?
Yeah, sure, I'll take that one. So for anyone who doesn't know what cultured meat is, it's a way of growing meat without the animals involved. Well, they're involved very small amount at the beginning. So there's a type of cell called a stem cell, and that's the stem cells are what all of our body cells grow from. So in the embryo, that's made up of stem cells which grow and divide and develop into all of the cells that make up our body. And as an adult, you do still retain some stem cells. So in our muscles, we have muscle stem cells that can develop into any one of several different muscle cells. So to grow meat, we isolate these stem cells either from animal embryos or from animal muscle. You just need a couple of cells, which you then grow up into, well, a meat goo. And this can be grown on a 3D scaffold so that it can mimic the texture and structure of meat. And yes, as you said in the comments, there's a lot of benefits to this. So there are very, very few animals involved. You just need a donor animal to give their cells. So that saves a lot of space. All you need space for is these big tanks called bioreactors, which are what you grow the stem cells in. So uses less land, and the potential to reduce the greenhouse gas emissions and the amount of water that's used to produce animals conventionally. Also, you don't need to worry about disease of animals. So a lot of the animals that we bring up for meat or other animal products, they'll die or get ill so that their meat is wasted. And so firstly, we don't have that animal loss. And then secondly, we also don't have to use antibiotics because it all takes place in a sterile environment. So that gets rid of a lot of the issues associated with antibiotic resistance growing from animal farming. So yes, that's a lot of positives we can see with cultured meat. There is the problem that it uses a lot of energy at the moment. because the bioreactors, the big tanks that the cells are grown in, require specific conditions that you need energy to maintain. And also the solution that the cells are grown in is quite expensive, well, not quite, it's very expensive, and also requires quite a lot of energy to produce and isolate the right molecules for it. And it is getting cheaper and less energy intensive. As we turn to clean energy sources, then this will be less of a concern for the climate impact. In terms of the cost, it's come down massively in recent years. It's still quite a lot more expensive than actual meat, but there's a lot of exciting innovation in that area. And so who knows, we might start seeing cultured meat in our supermarkets very soon. So it's an exciting, watch the space. Don't put all your hopes on it, but yes, it could be there very soon.
Yeah, this is just another case. You see this, if you really look into the details, the very details, not just at the news titles, of the science and research and engineering that has been going on in the last decade, you will become a climate change optimist. Because there's just so much that is happening that people aren't aware of. That things are getting so much better so quickly. And I like this solar graph so much because it shows something that's really important. When solar is 100 times more expensive than coal, no one's going to use it. But when you make it 10 times cheaper and it's only 10 times as much expensive, still, no one's going to use it. And if you make it another 5 times cheaper and it's only 2 times as expensive as coal, nobody's going to use it. But once it crosses that line, and it's just a tiny change, once it crosses that line, it will explode. And people will start using it all over the place. And there are a lot of technologies that are just early on this curve. They're early on the price reduction, in the scalability, in the sustainability development. And we've done it in the past. We've developed technologies, we've made them scalable, we made them cheap. Now, there's no reason to believe that we can't do this with other technologies. Nobody would have guessed that this phone would exist in 1900, or even in 1950 or 1980 or 2000, for that matter. No one. And well, maybe in 2000, but not in 1980. The people wouldn't have guessed that. And we wouldn't guess what's going to happen in 30 years. But you and we are the people that are responsible for seeing that trend before it happens and making it happen. Innovation doesn't happen overnight because we want it to, or because it's some curve that just naturally decreases. It happens because smart people work a lot and they have good ideas. And then they turn them into reality. They build them, they test them, they fail, they try again, and then sometime it works. And that's what decreases this curve. Sorry, just a bit of motivation. We're going to get cultured meat probably. It's going to take some more work. We're going to get clean energy. It's going to take some more work. If you're the kind of person who really wants to contribute hardcore and you're in the right age to pick a job, this is the time. The next 30 years are going to be the most exciting about climate change solutions ever, because this is when we're going to solve it. We are going to cross all of those lines in the next 30 years if we throw that brain power and funding at it. And I believe we will. The public awareness is there. Climate science is trying to do the job in convincing the public, and especially students, that their work matters and has immense impact over the next few decades. And we're also, on another hand, trying to convince governments that they should spend more money on it. But that's a less public discussion. Yeah, but I just wanted to put that out there. Your work can have an enormous impact, right?
I think it was Jonas's question on can working on climate change assist with tackling other issues that we have nowadays? And I think that's something very true, is that nowadays, sorry, I got distracted. Nowadays, lots of issues are actually related to climate change. So for example, developing countries, by tackling climate change, we're actually helping a lot of developing countries, because developing countries are often the countries that are the most at risk of the impacts caused by climate change. But tackling climate change also goes hand in hand with other things like gender equality and education, because as we were saying earlier, a big problem with climate change right now is that we need more researchers doing research and learning, like finding solutions to this. And if you think about it, if you have countries where women are not being educated, or just the entire population is not being educated, that's a whole groups of people who are not available to use their brain power to solve these issues. And that's why I think it's really important that climate change that we make sure that climate change goes hand in hand with other issues. And I think it's not even that we need to make sure that it does, it's just that naturally other issues can benefit climate change. And this also ties into other things, like, for example, a lot of people say, well, climate change and economic growth don't go together, but that's not true. Climate change is in itself an economic market, where there's a market for new solutions, for new technologies. And there's just so many of today's problems and just issues that we're working with are tied with climate change and have an impact on it, really.
Right. Thank you, Joe. If I'm not mistaken, I believe this was the last question. I really hope we didn't miss one. If we missed one, I'm going to wait 30 seconds now. Tell us in the chat. It was not on purpose. We try to answer every question. So if we missed a question, please just tell us in the chat, and we'll answer it now. Otherwise, I think we got it. High five, people. Right, yeah. Beatrice, thank you for saying I'm loving the optimism and the excitement. This is partially what is really exciting about working on climate science. You see that like if the future looked daunting and we really didn't see a way to solve it, I think we'd all be depressed by now. But luckily, the more we read into the science and into the research, and I personally enjoy reading patents that have been filed. It sounds weird too, but I enjoy reading patents that have been filed by research organizations and companies in the last few months, just to see how fast it's moving. And some of them are just incredible. Like, they're solving problems that 6 months ago were unsolvable. So whenever someone tells you this is technologically unsolvable, and we need X, Y, Z, and technology can't do it, I think people are vastly underestimating technology, but also some things are actually impossible. And there is an easy way to figure out what's impossible and what's not. Just sort of try to look at it like, solar panels will never harvest more than 100% of the sun energy that hits them. There's just no way. That's the amount that hits them. So we'll never make more than that. However, that's the area of Germany that you need. Then that's okay. So running calculations like this on first principles, for example, told us that carbon removal from the air is very unlikely to ever have a large impact unless we do it over hundreds of years and once energy costs basically nothing. So there won't be any direct air capture until maybe 2100, even 2200 potentially. That matters. We might remove a few tons just to get news headlines by some companies, but there won't be any large-scale removal. However, that might get relevant later on. So running these so-called first principle calculations really is motivating, because you see what's technically possible. We're just not there yet. And if you run the 1980 analogy, think 30 years ahead, yeah, that is motivating. And I think people should do it more rather than just listening to sort of the linear everything is going to stay the same and we just have to not use anything. I don't think that's the truth. And I believe that, yeah, I agree. That's very motivating. Right. Okay. No one said we forgot a question. So thank you all for joining in the name of all of climate science, not just the three of us. Again, I want to emphasize that we're just three faces, or four with Christian for a short time, that you're seeing. There is a large team behind climate science, and all of them deserve to be named and honored. So check out the website. Check out if you want to join us. There is a way to contact us from the website as well. Send us a message if you're not already, didn't already, based on our hiring post that we posted 2 days ago. But yeah, thanks for joining. Anything else?
And if you're interested in learning more about climate science, check out solve.climate-science.com. I will send a link in the chat right now, because that is where all of our content is and where we will be adding more content in the coming months. So make sure to check it out, because there's so much more content that you can just learn from. And feel free to reach out to us if you have any questions or just anything like that, because yeah,
that's our job. Great. Right. This is it. Good work, guys. It was fun.
Okay, great.
Do I just end this stream now? I think so. I don't know how to.
Yeah.
Back to newbie YouTube phase. Let me go back to the dashboard. I got it. Okay. See ya, people.
Bye.
Bye. And we are out.